So this is third session of the day. Thank you all for coming back. Our presenter is named Ryo Okamoto. Yes. Apologies. He's with RKI Instruments, which is a subsidiary of Riken Keiki Japan. He's worked there for 18 years. He's vice president of sales development, holds a bachelor's degree, and counts fishing amongst his hobbies. I'll turn it over to you. Thank you very much.
Thank you. Thank you for joining us. My name is Ryo Okamoto from RKI Instruments. Since this is the first time for us to present at the ATC, let us introduce our company first briefly. RKI Instruments is a subsidiary of a Japanese company, Riken Keiki, who is a manufacturer of calorimeter, gas detector, and gas sensors. And they have a history for 85 years. And then there are like 1,300 people working dedicatedly for the gas sensing technology. And the RKI is located at the San Francisco Bay Area. We are about 100 people. We do manufacture some products in US, and also supply the products to the customer and provide the service, like installation work and then calibration work, etc., for the US customers and North American customer. Today, as you can see on the screen, I'd like to talk about the calorimeter, which US people tend to call it as a BTU monitor. And then mainly focusing on the flare stack gas monitoring, and also introduce some other applications. Okay. So here is agenda. Number one, I will talk about the various applications of calorimeter and the market trend and the new regulation and the technology comparison. And the number two, I will focus on the sensor principle explanation using the optical sensor and the sonic sensor, what we call optosonic sensor. And number three, I will introduce about the application with some test data. And then number four is a conclusion. So here, there are various applications of calorimeter. And then I'm not going to explain everything, but I will talk about the flare monitoring, which is performed for the safety and the environmental monitoring purpose. And also, I will talk about the carbon neutral, which the like hydrogen and then ammonia are considered as important energy. And then also talk about the refinery gas, refinery fuel gas for the like a boiler control. And also talk about the natural gas pipeline price determination application. But the message, I'd like to emphasize the calorimeter is used for the various applications in the field. And we supplied our products to the field. And then there's a market trend. The hydrogen is considered as an important energy. And then there are some new applications like a hydrogen steel making, and the fuel cell, and the hydrogen refueling station, hydrogen station, and then gas turbine for the hydrogen blended fuel. So the increased demand for the hydrogen makes more demand for the calorimeter. And for the calorimeter, it is getting more important to measure the hydrogen as accurate as possible. So this is about the new regulation in the US. EPA issued an updated refinery sector rule on March 2024, introducing the stricter regulation on the flare gas emissions. The goal is to reduce the greenhouse gases and the air pollution. And there are 4 key points. 95% combustion efficiency, which requires a stable ignition source and the sufficient heating value of flare gas. And then gas monitoring, so real-time monitoring of BTU is required. And the visible emission monitoring, so visual check and the cameras, using the camera is required. And also tip exit velocity control need to be more stable. So these are 4 points on this new regulation. And then gas monitoring parts, the calorimeter is strongly related. And this is a table comparing some technologies commonly used in the flare gas measurement. And then like these are items to be compared. And then I'll try to explain the optosonic sensor first. So accuracy is like a 2% for the flare gas. And then this is a continuous measurement. And since we use a physical sensor, there is no calibration required in the field. So there is no need to calibrate the sensor for more than 10 years. So the continuous measurement is very good for this sensor. And the high-speed response, T90, within 5 seconds. And the running cost, we don't have any optosonic sensor, doesn't have any consumable, so customer doesn't need to replace the consumable. So the running cost is good. The weak point of this sensor is gas composition analysis. It's not available for this sensor technology, just BT monitoring. And the other required utilities, instruments air or nitrogen is required. And next is a gas chromatograph, GC. Accuracy is quite high, but it's not a continuous measurement. And then our response is not very fast. And then running costs, there may be some consumable need to be replaced, and then calibration is required. But the strong point is gas composition analysis. But carrier gas, like helium, is required for the measurement. And then residual oxygen, which is quite popular for the flare gas measurement. The accuracy is good, but the frequent calibration is required, and then high-speed response. And then calibration is required, so the running costs take higher, and then instruments air is needed. And dense meter, the accuracy is not so high, but it's a quick response and the measurement is continuous. There are some spare parts needed. So that's a kind of comparison for the flare gas measurement technologies. Now I would like to talk about the calorimeter, optosonic-based calorimeter. And the product name is OHC 800. As you can see on the left side, the enclosure has a sampling system, which is for the two lines, one line for the sampling gas, the other line for the reference gas. And then this is an explosion-proof unit. And then, as you can see on the right side picture, there are four modules installed in the enclosure. And then there is an optical sensor for measuring the refractive index. There is a sonic sensor for measuring the sound speed. There is a main controller, and then there is a terminal module. And then there is no tube internally, so it's a tubeless design. And then each sensor, these are calibrated at the factory. And then since these are physical sensor, once we calibrate the sensor, there's no recalibration required at the field. And then, as you can see, there's just screws to fix the sensors. So once some issue is caused on the sensor, just a quick swap is conducted by the customer. It's like 10 minutes. So this unit minimizes the downtime in the field. Okay. And this is about the sensor principle for the optical sensor. Again, this optical sensor is to measure the refractive index of the target gas. And then there is a relationship between the refractive index and the calorific value, BT value. So if we measure the refractive index, then we can measure the BTU calorific value. And then, as you can see on the structure, there is a measuring gas chamber here and here, and then there is a reference gas chamber here. So sample gas is filled in the measuring gas chamber, and then reference gas is filled in the reference gas chamber. And then, since this is an optical sensor, we have a light source here, and then one light goes this way to this path. The other light source, which is separate at this point, goes this way. And then at this point, the separate light source merge again. And then this is the physics, but the interference fringe, like this, is generated. And then we watch this interference fringe on the CCD camera set on the sensor. And then this interference fringe moves in proportion to the difference of refractive index between the measuring gas and the reference gas. So simply say, like, if there is a high BTU gas come into the sensor, this interference fringe moves from actually left to right. So higher BTU value, more movement. So this is how the optical sensor works. Oh, and then the light source of the this sensor is LED, so its light lasts for very long period. And since the wavelength of the light source and the chamber length in the sensor is stable, there is no like sensitivity changes after the calibration at the factory. So this is about the sonic sensor. Again, this sensor is to measure the sound speed of the target gas. And the same as the optical sensor, we know the relationship between the sound speed and the BTU value. So if we measure the sound speed, then we can measure the BTU value. And then here is a chamber, and the measuring gas filled into the chamber here. And there is a sound source here. This is a sound receiver. So sound emitted from here to here. And then this sensor measures the time the sound travels through from here to here. And then if the gas with the BT value filled in the gas measuring chamber, the light source, sound speed gets slower. So we monitor the speed of sound to measure the BT value. And the same as the optical sensor, this sensor is based on the physical, so no chemical reaction and the burning, so the sensitivity is quite stable as well. And then this is the sensitivity of the optical sensor. So as I mentioned, if we know the refractive index, there is a relationship between the BTU value. So, for example, this is a methane pure gas, 100% methane. So the refractive index is like a 400. So if we measure the 400, the device indicate like a 40 megajoule, which is about like a 1,000 BTU. And then the straight line from here to here shows the sensitivity curve. And as you can see, like methane, ethane, propane, butane, these are on the sensitivity curve. But as you can see, like blue gases here, for example, CO2 doesn't have a BTU, but the CO2 has a refractive index. So once CO2 is, for example, pure CO2 is measured, our optical sensor measure as like a pure methane, and it shows like a 40 megajoule, 1,000 BTU on the display. So that was a kind of character, and then that was a kind of issue we faced before. So even there is no BT value, but optical sensor itself showed like a 40 megajoule as like a methane pure gas. So we had a lot of interference effect by the inert gas. And then same for the sonic sensor. We know the relationship between the sound speed and calorific value. And the same as the optical sensor, this is a sensitivity curve. It's quite linear for the hydrocarbons. But the CO2, for example, is pretend as a, interference gases. But Rick and Keiki found the relationship between the two sensors, between the optical sensor and the sonic sensor. And then what they found is a kind of distance from the sensitivity curve to the interference gas, like a distance from here to here. Like a CO2 distance is like here, but the optical sensor distance is like here to here. The other gases were like O2 and nitrogen. The distance is here and here. This is sonic sensor here to here. So these two sensors have a similarity, like a length of the distance is like a 2.2 times longer for the sonic sensor. So there is a similarity between the sensor. So if we know the similarity, then we can apply the formula to calculate, to compensate the sensitivity. So now, using the calculation, like all target gases are on the sensitivity curve. So even there is a CO2 contained in the sampling gas, we have no influence from the CO2. So that's a kind of improvement the Rick and Keiki achieved 20 years ago. All right, so more specifically about the flare stack monitoring. So this is the test data that Rick and Keiki had for the flare gas application. There are two groups of gas, high pressure gas and the low pressure gas, and then each group has a 3 target gas, and then gas component is mentioned here. But measuring these 6 gases, the accuracy, this is a calorific value, is a theoretical calorific value. And this is a measured calorific value by the OHC 800. But there is a close measuring result. And then, as you can see here, error is quite small. And then good thing on this application, the measuring range is quite wide. Optosonic sensor can measure 0 to 2800 BTU, which can cover the low pressure gas and the high pressure gas, both with the one sensor. So using the one sensor covered 2 type of your target gases. That's a strong point of this principle. And the next one is refinery fuel gas. There are 5 types of gases here, like methane with hydrogen, and then methane with interference gases, like inert gases, CO2 and then nitrogen with hydrogen. And this is a HC hydrocarbon, lower value and a higher value. And then these are with the interference gases, nitrogen and CO2. And then this shows the result of the measurement. And then most of the target gas are within the 2% accuracy, except the gases with the 30% hydrogen with the hydrocarbon rich gases. So this one shows 2.7%. This one shows the 2.7% accuracy. But other than these two gases, the accuracy is quite high. And this is the application for the carbon neutral. There are some application for the ammonia decomposition process. The customer need to measure the ammonia, nitrogen, and the hydrogen at the same time. And then we know the relative density, it's a density, kind of sound speed. And then we know the refractive index of these three gases combination. So if the target gas is just limited to 3, we can accurately analyze the concentration of each target gases. So this is a quite new application for our sensor. Accuracy is at 1%, within the 1%. And this is for the natural gas pipeline determination of transaction price application. We can measure the BTU value, and then also we can measure the compressibility factor at this application. But officially, gas chromatograph need to be used for measuring the compressibility factor. But using our sensor, optosonic sensor with the IR sensor, then we achieve very close measuring result with the GC, like this. The blue point is actually it's opposite. It's a GC, and then the line is optosonic sensors. So we track the value measured by the GC. And the accuracy is within the 1%. Even the hydrogen is included in the sampling line. Okay. And this is the last one, but it's a steel byproduct gas measurement. And the steel, there are like a coke oven gas and the blast furnace gas and the converter gases. There are some recovered energy in the steel industry. And then we have a technology to measure the BTU value and the gas component of these 5 gases listed here. And the accuracy is within the 2%. So traditionally, the GC is used for this application, but we can substitute the application with our technology. All right, so this is the last slide, the conclusion of the optosonic sensor. We have a high-speed measurement within the T90 within 5 sec. And then we have like a 2% accuracy for the Freya stack application, and some others like a 1%. And we are the real-time measurement, and you don't need to worry about the calibration in the field for more than 10 years. And then, OIML. This is the European certification for the natural gas pipeline application, but we got that certification. Then the last one is the robustness. Since we use a physical sensor, the sensor lasts for more than 10 years without changing any consumable. So it's quite robust sensor. So that's a summary of the optosonic sensor. Thank you very much.
Does anybody have any questions for Ryo? Yes.
How long it takes for a single measurement?
How
long it takes for a single measurement?
Single measurement.
How long?
The measurement is within it's like a 5 second. 5 seconds for the like a total 90% response. It's a quite quick response.
Any other questions?
Hi, Ryo. You showed us a plot of the calorific value versus the refractive index and calorific value versus the speed of sound. Would you be able to tell us what the uncertainty of the measurements of calorific value, what those might be in the order of? And I kind of missed how you went from individual speed and sound into a combined one where all of a sudden the carbon monoxide, the oxygen and nitrogens, they were now on the same line. You could explain that.
So you talk about, already the lines cut. I'm sorry. The
calorific value versus the speed of sound. I would like to know the uncertainty of those measurements.
Yeah.
The calorific value. And how you went from individual sound and
just it's a kind of calculation. So like an optical sensor itself measured like a direct measurement for the refractive index. Sonic sensor measure the sound speed, right? Yeah. And then we calculate the measuring results. And then we output the like a calculated value on the like a display. So it's a kind of like calculated. Okay. Sorry.
Yeah, they actually have there's a different slide that's in a different slide deck that shows the calculations for the optical bench, and then the calculations for the sonic bench, and then they basically solve simultaneous equations to develop a constant for the components, the non-BTU contributing components.
so that's how they were able to be on that one line.
Right, right.
All right. Well, in the interest of time, I think we'll carry on. Thank you very much, Ryo, for your presentation, and we'll call up Trevor Tilmann, please.
Thank you very much.
All right, our next presenter is Trevor Tilmann. He's with Thermo Fisher Scientific. He's an applications engineer. He began his career in 2017 at Montrose Environmental Group, performing FTIR emissions tests for a variety of industrial sources. He's been with Thermo Fisher Scientific since 2023 as an applications engineer focused on developing clean energy applications for the process FTIR product line. He specializes in gas analysis, method development, and continuous emissions monitoring. His hobbies include training his bird dog, fly fishing, golf, archery, and skiing. Busy guy.
Yeah, a lot of hobbies. All right, hello everyone. Today I'm going to talk about, sorry if this is too loud, real-time analysis of CO2 purity for quality assurance in carbon capture and storage using FTIR spectroscopy. So first I'm going to talk about the key driver behind CCUS, and that is the greenhouse effect. So the greenhouse effect of the Earth's atmosphere is to absorb infrared radiation from the sun. Certain compounds, such as water and CO2, have the greatest rate of absorption and the radiation of heat. They effectively trap the heat in the lower atmosphere and result in the moderate temperatures that we all experience. Since the mid-20th century, atmospheric levels of carbon dioxide have risen consistently year over year. This has resulted in a direct correlation to the planet's average surface temperature, which has risen over 2 degrees C over that same time period. Since 2015, countries and corporations have set greenhouse gas emission reduction goals that are pretty aggressive. So we're reducing greenhouse gases by 2030, and then with the ultimate goal of being net zero by 2050. CCUS is a process that will help mitigate this. Once the carbon dioxide is captured, we can either utilize it in applications such as beverage carbonation or enhanced oil recovery, or we can permanently sequester the CO2, preventing release from the atmosphere. That's kind of, the evidence of this is the operational facilities. So there's roughly 50 globally right now, and that number is expected to grow to, I know it says 500, it's actually about 630 by 2030. There's already been over $6 billion invested in CCUS, and that investment is expected to grow to an annual investment of $175 billion by 2035. Majority will be in the hard to abate sector, so basically material generation or power generation, and that's kind of outlined on the chart on the right. If we look back in the past 10 years, 20 years, we see that CCUS has only been used in natural gas liquefaction as kind of a byproduct. But looking forward in the next 5 years, we're seeing the diversity of industries adopting CCUS growing drastically. You'll see in green here, that's hydrogen ammonia production. So for blue hydrogen, carbon capture is implemented right into the methane reformation. And basically, that level of investment right now, just in CCUS, is not going to be enough to meet the 2050 goals of net zero. We're still going to need eventually either green hydrogen or some other clean energy source. CCUS is kind of the step to get there. So how is carbon captured? There's 4 main ways that CO2 is captured. I really want to highlight that each of these capture techniques does have the potential to introduce impurities into the captured CO2. It's also dependent on the industrial production method. Say combustion, where CO2 is captured, is going to have an entirely different impurity mix than just ambient air capture. So going through these, pre-combustion capture, this is using fossil fuel that's partially burned to form a syngas. Syngas will then be put through a water gas shift reactor and then creating pure products of hydrogen and mostly pure CO2. The hydrogen can be used for power generation, and the CO2 can be used for either utilization or storage. Post-combustion capture, this is probably the most common that we see, mostly because it can be retrofitted directly into industrial processes. But in post-combustion capture, we basically take the flue gas, we'll route it through a solvent-rich bed, usually are amines at this time, that have a special affinity towards carbon dioxide. The amines will, or the amine and carbon dioxide mix will then be heated to separate the carbon dioxide, and then it can typically be transported. Next is oxy-fuel combustion. So this is basically removing the air out of the equation with combustion. As everyone probably knows, when we combust with air, we have a lot of opportunity to create oxides of nitrogen. Combusting with pure oxygen results in an almost complete combustion reaction. So our main byproducts are just moisture and water. The moisture can be easily dropped out, and then we have captured CO2. And then lastly, for direct air capture, this is something that can be implemented, say an industrial process is not on site. We could take land basically and suck carbon dioxide directly out of the air around us. There's only about 400 ppm, so we need a lot of volume of air to capture CO2, but in utilization cases, this is definitely a lot cleaner than, say, combustion capture. So here I'm highlighting some of the critical impurities that could be present in a carbon capture stream. The main issue that we see is a lot of the existing oil and gas infrastructure is still using carbon steel pipelines. Nothing has really been changed for these sequestration sites, and the opportunity for these impurities is a little bit different than, say, transporting natural gas. Carbon dioxide itself can react with water and create carbonic acid, oxides of nitrogen and sulfonated species, and water and oxygen kind of all tie into this nitrogen oxide cycle where we can readily create nitric acid and sulfuric acid. Also, using supercritical CO2, we are pressurizing the components to a point where we're shifting the phase kind of towards the liquid state, so we can get a lot of goofy reactions taking place within these pipelines. You'll also note that there's certain components, I have methanol outlined here, but also glycols. Those will create kind of buffer conditions for these acid reactions to take place. So it's a lot more important stream to monitor continuously than, say, just a typical natural gas stream. So that kind of ties into why continuous monitoring these streams are as important. The biggest key is safety of company assets. There's basically going to be a custody transfer from the industrial process that's capturing the CO2 to the transportation network. We're monitoring all of these impurities in real time to verify that they do not exceed the limits that'll put the company assets at risk. The next most important reason is for the absolute purity of CO2. This ties to the tax incentives associated with permanently sequestering CO2, whether it's the emission trading system in Europe or a greenhouse gas offset here in the US. We are required to monitor continuously because these processes are expected to be very transient. So in Europe, for example, you have multiple industries tying into one common pipeline. So you could have hydrogen production and then oil and gas production tying into the exact same pipeline. Upsets in process or shutdowns, stuff like that, could drastically change impurity levels that are present. The last two they kind of tie back to the absolute purity of CO2 that must be measured. We really need to characterize this entire sample to get an accurate idea of the flow dynamics within it. If we do not have an accurate flow measurement, we're not accurately measuring the total amount of CO2 that is sequestered. That brings me to some of the measurement challenges for analytical technologies. We know this stream is going to be very high concentration. They're typically 95+% CO2, and the requirements for the impurities are usually less than 10 ppm. In some cases, they are closer to 1 ppm for each individual one. And there's also a lot of potential for additional unknowns to be introduced into the process over time. As carbon capture technology continues to grow, there's probably 30 different proprietary amines that are used right now. It's going to continue to change over time, so there's not really a common set right now. Next is the limits of detection. I already mentioned that it needs to be measured in low ppm, but it kind of ties back into There's not an established global specification at this time for CCS matrices. In Europe, it requires, which you'll see, up to 30 components. In the US, it could be 8 components. It's not really established at this time. And then lastly, a lot of these monitoring points are going to be in remote areas. They really require hands-free operation and minimal downtime. The CO2 will be traveling at about 4 to 6 meters per second, so it's really important that we have real time and can stop the flow if needed. So here are some of the typical CCUS measurement points. We can start at number 1. This would be the outlet of an emission source. So even if the CO2 is captured, we're still going to have a common emission source that we will monitor for any breakthrough. Next would be the inlet and outlet of a CO2 capture facility. So measuring both of these will allow the facility to gain insights on their capture efficiency. 4 will be basically strategic points along compressor stations throughout the transportation network. Even small changes in elevation are expected to change the phase within these pipelines, so very important that we monitor consistently across. 5 would be CO2 storage facility. So say the CO2 is going to be utilized for something such as beverage. We would verify that in the storage facility. 6 would be, say, an onshore facility. So basically where the ultra pressurization would take place before it's transferred to its permanent sequestration point. 7 is loading and offloading station. So this is very common in Europe for industries that are completely landlocked with no access to a permanent sequestration point. They have converted liquid natural gas ships that they ship liquefied CO2 with. And then lastly is the injection point. So here's a typical specification that you will see. This is a specification from Aramis in the Netherlands. Aramis is tasked with designing the transportation network for Porthos out of the Port of Rotterdam, also in the Netherlands. And you can see here the component list compared to a majority of the US specifications is a lot more stringent. This was selected for the study because at the time it had the lowest requirement for NOx. You can see here it's less than 2.5 ppm. Since then, and that was about a year ago, it's changed to less than 1.5 ppm. But we see a lot of volatiles must be measured in low ppm. We see high levels of hydrocarbons as well. So you have up to 1% methane and then around 1,200 ppm of aliphatic hydrocarbons. So this makes a very difficult mix to measure. So for the purposes of this study, I focused on the columns on the left. I'm using FTIR. All of these are nice FTIR gases. You'll notice oxygen is on here. So the instrument that I'm using is an integrated system that does contain an oxygen analyzer. So that was also assessed. So I'll get into the experimental setup a little bit. So the tests that were performed, we performed a limit of detection assessment. This was using the actual expected sample matrix, not just, say, CO2 or nitrogen. So we basically simulated a stream of greater than 95% CO2 and then greater than 0.3% methane to really show the capabilities of the quant regions. Next, we showed accuracy and linearity for NO, NO2, SO2, and CO2 itself from non-detect to a 10 ppm range, again in that diluted sample matrix. The next test was a 14-day drift for absolute purity. This is basically just showing calibration stability of the CO2 measurement. And then lastly, a third-party lab performed an interference test using moisture at varying levels across the specified range. And all this was performed on the Thermo Scientific MaxBev CO2 purity analyzer. It is included with a fuel cell oxygen analyzer, so that's where you'll see the oxygen results. So here's a summary of the results of the limits of detection compared to the specification. You can see our 3 sigma results in the sample matrix are well below the specified limits, even with the high concentrations of potential interference and high levels of CO2. So we're roughly 20 to 50 ppb, or 20 to 50 times lower than the specification, which allows us to have a lot of faith, especially in, say, the specifications were to be lower over time. It allows us to feel confident that we're going to be ready for that. Next, for linearity, you can see here across the specified range of 0 to 10 ppm for each of the impurities, we showed good linearity. Linearity is always important to show kind of the transient property. It allows us to have faith in our calibration that we can hit the points as the concentration is changing over time. And here's kind of a summary of everything. You'll note the STAR components, those were not tested during this study, but overall study kind of verified that an FTIR is a viable solution for measuring these with high accuracy and precision. So next, 14-day drift assessment was performed on the CO2 absolute purity. This was performed with research grade CO2. Basically, a background was taken on the FTIR, and then nothing else was done over a 14-day period. So this shows the lack of drift that FTIRs potentially can have in these measurements. All of these points are within plus or minus 0.02 of the expected of 99 with 4 nines. So we see a lot of calibration stability, and like that's kind of important for monitoring these streams, because the biggest thing we see with other technologies is the amount of downtime just from calibrating. For systems such as this, it could potentially go months without recalibrating. And the last performance study was the interference test that was done by a third-party laboratory. So this was basically a ramping of moisture from 50 ppm down to 10 ppm to see the effect, if any, on additional components. And overall, all the impurities that were measured were unaffected by moisture, which is good because moisture is usually, from an FTIR standpoint, a primary interferent, moisture and carbon dioxide, but minimal effects from moisture, which allowed us to have very confidence in our results. So lastly here, just hitting the conclusion, I talked about CCS and its driving force behind it, which is offsetting greenhouse gas emissions. It's incentivized by government regulations and corporate sustainability goals. Really wanted to highlight the impurities that can be introduced both on the capture technique and the industrial production method. And then overall, FTIR has been verified as an effective tool for monitoring these streams. It meets the low impurity limits, at least in Europe. And once we get an established specification, I anticipate it'll also meet that here in the US. And yeah, minimal cross interference and long-term stability. But that's all I have. Thank you very much for listening to me.
Thank you, Trevor. Any questions for Trevor? Yes. Why'd you sit so far away?
Great, thank you very much for the presentation, Trevor. I was wondering if you talk a little bit about the sample handling considerations or challenges that you had in this project.
Yeah, so definitely rely a lot on integration, specifically with vaporization and pressure knockdown, because when we're going from over 100 bar down to we're running at pressure a little bit, so it's usually handled on integration, but That's probably all I can really say there is, yeah, there is definitely challenges knocking it out, and maintaining sample integrity, getting it to with an extractive analyzer is a definite challenge, but we've seen a lot of success going from supercritical to gaseous, but basically vaporization, pressure knockdown, all of that.
Any other questions?
No, just a quick question. I was noting that you weren't measuring the nitrogen, which is not a small concentration. Does that impact the precision over time, do you think? Or is it constant enough where it doesn't really impact all the calculations?
You said nitrogen?
Yeah.
Yeah, so we're only measuring the infrared active gases, so we do have the supplemental oxygen analyzer just for that diatomic, but we'd recommend usually an integrated solution for the entire specification. So, yeah. But yeah, no, nitrogen is definitely important. It fills the pipeline capacity, so it'll be measured, but just not with an FTIR. Yep.
Anything else?
Okay.
At what level will moisture become a problem as an interference?
Yeah, so I'm calibrated up to 200 ppm right now. That's kind of our dynamic range with the pressure set point that we're operating at. Usually I will not recommend going above that, not due to interference so much as it's very hard to calibrate a gaseous phase mixture running at pressure. So that's generally our range right now is up to 200 ppm, nothing beyond.
Very good. Thank you very much, Trevor. Appreciate the presentation. Before we call up our next speaker, we have a special announcement, and I'll call Paul Barnard up.
Thank you, JC. As you're all aware, this analyzer community has a partnership with Lee College, and I'm not going to steal the thunder of these guys. I'm going to let Wes explain what's going on right now. We have staff members from Lee over in the red shirts, and we've had students up from the college here this morning. What we'd like to do is introduce to you all is the term president of Lee College? Chancellor. President.
Stand corrected.
Some big shot from Lee College is here, okay? So we're here to introduce her to our community and to make an announcement, and I'll pass that over to Wes.
And I'm going to pass it to Dale because I get tongue-tied.
Well, on behalf of this community and on behalf of the executive board of ATC, I'd like to present you with this letter of intent to contribute $30,000 to Lee College in mutually agreed terms between the college and us about what the money is to be used for and where it's supposed to go.
Oh, thank you. Can I hug you?
Yes, you may.
And to hug everyone else? I feel like
These funds are derived from this event and previous events that we've been able to fund this.
Sure. Good afternoon, everyone. Oh my gosh, is this the post late lunch slump here, or not enough coffee? Well, at any rate, my name is Linda Villanueva, and I'm the president of Lee College. I'm here because you guys are all making a difference in the world around us, in our region, and in our communities. So I'm often told, and I often say to others, that The students at Lee College and anywhere else don't come to us because they want to earn degrees or certificates or to transfer. They want to come to Lee College, and they do because they want to improve the quality of lives, their lives. And what that means to us is we work very strongly with industry to ensure that we are connecting them with jobs and careers that are going to provide high labor market outcomes that will help them to sustain them and their families. And that's a big deal because when you look at our college, you may not know this, but 73% of our students identify as having at least one unmet basic need. And for our students to be able to be connected to filling the talent pool that you need in this very important area is allowing them to break generational poverty, addiction, to become part of our educated citizenry, and let's face it, especially when I'm talking to legislators, to become taxpayers and not tax recipients. I'm sure you're aware of our standing in the Gulf Coast area. If you just look at, for example, our biggest industry is the petrochem complex, right? And hopefully you guys know that petrochem complex right here, just along the 26 miles and in the adjacent area in the Houston Ship Channel, one, it's the largest complex in the world, okay? And then the second, I don't know if you know this or not, but that 26 miles produces 20% of Texas's GDP. That is huge. The third thing I will tell you is it also provides 1.5 million skilled jobs in this area compared to only 3.3 million in the same area across the entire nation. This area is doing the lion's share of the work in these critically important areas to improve and sustain our economy. But again, most importantly, I just want you to know that we're here to listen, to understand your needs, to build programs that meet your needs, especially as you're evolving, and to ensure that we are nimble, flexible, and graduating and preparing students that have the knowledge, skills, and abilities that you need to fill the talent pipeline that you have. So again, at the end of the day, though, it's all about supporting you guys and the roles that you have and your needs, but also improving the quality of lives for all that we serve. So thank you so very much for this generous gift, and thanks for letting me take up a little bit of your time. Have a great day.
Okay, so we're ready. Thanks everybody for that little change in the schedule. Appreciate it. Our next presenter is Serge Bays. His company is LimeSoft, where he's the managing director. His education is in software engineering. Serge is a seasoned entrepreneur and executive with over 16 years of experience building and scaling technology companies. As the founder of LimeSoft, he's grown a market-leading international business specializing in emissions monitoring, regulatory compliance, and process optimization software. Deployed in over 20 countries, LimeSoft's solutions support more than 10 Fortune 500 companies across the energy, natural resources, critical minerals, cement, and waste energy sectors. His work supports a cleaner, more sustainable future by enabling industries to measure and reduce toxic emissions while accelerating decarbonization. Outside of work, Serge supports startups through advisory, mentorship, and board roles at Tech Alliance Accelerator, mentors MBA students at Ivy Business School, enjoys reading, hiking, and participates in research on improving gut microbiome to treat diseases such as C. difficile, multiple sclerosis, and advanced pancreatic cancer. Please welcome Serge Bays.
Hello, everyone. Thank you for joining me here today. I know I'm the last person of the session, so I'll try to be quick and concise to let everybody get to the break. Today, I will be talking about software for analyzer control and emissions reporting. So it is a little bit different from the typical sessions here that focus deeply on spectroscopy, which I find incredibly interesting and fascinating, but I think it's still very much relevant to the interest of this conference and what we're all about here. So my topic is optimizing CEMS, which is continuous emissions monitoring systems for refinery SO2 reduction projects. And I'll open with a quick background and primer on the regulatory drivers and what necessitates these systems, and then we'll go into more details about how these systems work. So the first one you're probably very familiar with is US EPA 40 CFR Part 60 Subpart JA. That's been around for approximately 10 years, I'd say by now. And this regulation mandates the different emissions limits and continuous tracking of emissions from FCCUs, the boilers, the incinerator stacks for sulfur recovery units, etc. You can see here some of the limits that are mandated. There's different ppm values and different averages they need to calculate, as well as totals of the emissions. And they also mandate H2S, hydrogen sulfide limits for combustion device fuel gas, so things that go into boilers and heaters and appliances, as well as for the flare fuel gas. So to break it up a little bit, the first ones are your traditional CEMS, where you have the effluent post-combustion going into a stack, a small stack, and then being released into the atmosphere. And you have various analytical devices and methods to measure that. And the next part is the pre-combustion. Of course, you can't really measure the effluent of a flare because it's being burnt already in the open air. So we'll get into how we achieve that as well. The next one, this is the more recent one, and this is talking about more about US EPA and onward for the other global systems, is the Canadian OREG 88. That just came out approximately 2 years ago, and the mandated deadline has been extended. As we know with these regs, they get pushed back a lot until the end of this year. And typical of a lot of Canadian and worldwide systems, they kind of take what US EPA has done and copy it and build on top of that a little bit. So here we have similar things for the SRU, sulfur recovery unit incinerators. Now we have H2S as well as SO2 limits. So this mandates the refineries to be under 250 ppm on a 12-hour rolling average. You have fuel gas limits, not just for H2S, but for SO2. And the SO2 is calculated from H2S. The H2S usually in this fuel composition is the primary contributor of the sulfur. And you have flares as well. So you need to measure not just H2S, but other sulfur compounds that contribute sulfur to the total reduced sulfur that then gets converted to the SO2 post-combustion in the flare. So there's various limits and rolling averages on concentration, as well as total SO2 emissions per day, per quarter, and per year. Additional requirements are NHV, net heating value. So they mandate the refineries to calculate the net heating value for their flares, and depends on steam assist or non-steam assisted. And there's also requirements for pilot flame to be on for at least 14 out of every 15-minute period, and to measure flare tip velocity. And there's limits, and then alarms for that as well, should you cross that limit or that threshold. Now, although the main point of this presentation is the software that is at the heart of this large CEMS system that combines all these various sources and all the various analyzers, I wanted to briefly highlight some of the analytical equipment that was chosen. And different refineries with different types of combustion devices and configurations selected slightly different technologies based on their requirement to meet these regs. But some I wanted to highlight that were typical here. The SRU incinerators, the CO boilers were fairly standard, either UV or NDIR. TDL was actually used for some of the SRUs for like very hot and very like wet type of gas measurement. Flare, it's more of a pre-combustion measurement. So now we're measuring the actual fuel composition. And for this case, various technologies were analyzed. Most arrived at either GC, gas chromatograph, or mass spectrometry, and most decided to go with mass spectrometry for this application, for the fast response time test, as well as being able to multiplex and accurately measure the entire composition of the gas. And for heat or fuel gas, that's another pre-combustion, some facilities chose to go with GC, and most chose to go with TDL because they only wanted the H2S composition, and the ones that wanted the more detailed composition of the gas went with the GC. And for flow gas, either ultrasonic or optical flow meters were used when the stream was very hot. Now, one of the questions I received from the reviewers when I submitted my paper, and I appreciate it, so I wanted to quickly touch on that, was the CEMS DAS, which is the generic name for data acquisition system, versus the plant historian. So if we're grabbing all this data from all these analyzers and then we're trending and reporting them, can't we just use our historian for that? And the short answer is absolutely, you can, with enough time and effort. You can build a historian to accomplish all these various nuances of the regulation. So in this table here, I quickly highlight that a data acquisition system and a plant historian both gather all the data from all the instruments. They can generate various trend charts. Now, where it gets interesting is the CEMS DAS would be designed to have all the regulatory compliance reports that are associated with regulation, versus with historian, you need a bit of custom development. The analyzer control and validation, one of the requirements usually for CEMS regulations is daily validation, and if the validation fails the threshold, then you need to calibrate. And again, and multiplexing as well when we're talking about putting multiple streams in the gas analyzer. So plant historians typically don't do that. You would need some sort of a PLC or a custom DAS system that can accomplish that. Real-time compliance alarms, again, that's related to regulatory compliance. You can have, of course, various alarms, and then you can build custom rules for them, but it all comes down to how much effort you want to invest into building versus de-risking it and using something that's custom-made specifically for that application. We'll get into the system architecture overview really quick here. So as you can see, if we start at the top left, there's various flow meters that have, in this case, RS-482 communication, so serial protocol. We would just use a very basic media converter, convert that into Modbus TCP/IP. Then above, you have a mass spectrometer. In this example, for this type of instrument, we just use a direct connection over Modbus. And then for any type of instruments like pressure and temperature transmitters, we had analog and digital inputs that, again, went from that converter to digital Modbus. And when we're talking about controlling solenoid valves, we have a digital output. So it's going the other way. We're sending a Modbus signal to the converter, and that energizes various valves. And so all of that goes into the central data collection unit, which typically resides on a Class 1 Div 2 for this application hardware, a ruggedized PC that also has a touch screen on it, so it can work both as a buffer for many, many years with modern hard drives. It can be a controller that controls all the solenoid valve interlocks and NAD logic and calibration, purge, etc. And it also buffers all the data and then sends it to the central DAS server over a local area network through using TCP sockets. So when we talk about the data collection unit, the data logger, you can think of it as a newer take on the PLCs, and we designed it to be more robust and easier to maintain than the typical PLC setup. However, it can still communicate with various PLCs as required based on the facility. Then you can see various shelters. If we started at the top left, that would be, in this example, a flare shelter. Then we have a fuel gas shelter. One had a TDL system, one had a GC system. And then the top right, we have a boiler stack and an SRU stack as an example with similar setups. And various stacks, various shelters has various instruments on them. Each has its own dedicated data collection unit, which then are all centralized in a central DAS server, which has an SQL database. It has a redundant data collection unit. Because it's a software-based, now you can have a standby mode on the central server. So if the main data collection unit computer were to fail in the shelter, a backup one would be communicating with all the analytical equipment. And then once the main one is restored, the data is automatically synced back up. And all the data, all the raw data is stored for the lifetime of the project. So we're not reducing measured data, which we collect in with around 10-second interval, depending on the instrument. GC would be a little longer. We're storing all the raw data, all the raw alarms, and then in real time, as we need to trend data or generate a regulatory compliance report, we recursively build that out. So from measured value, we build 1 minute average, we build validated 15-minute averages. From that, we validate 1 hour averages, and then we have all the custom rules for the regulations I mentioned earlier, like rolling 3-hour average, 7-day average, and even like 365-day 1-year average. And with that method, if we're talking about redundancy, whenever the data is synced over, it's automatically processed. So there's no need to do any additional maintenance or reviewing the data and trying to match how the data works together. Also, to highlight here from the central data server, from the central DAS server, we send the data to the plant DCS, and we also have remote operator workstations located at various points depending on the facility setup and their cybersecurity requirements. This is an example DAS main screen. So different facilities, of course, have their own custom different screens depending on what it is. In this case, you can see here on the left-hand side, we have the various sulfur species, so H2S, COS, CS2, and this is for two streams, so 2 flares. I believe in this case, we're using 1 mass spectrometer to multi-stream 2 flares just for cost savings. And it has your real-time data, your 1-hour validated averages, everything's color-coded. Yellow is like a warning, red is more of an error. Error usually typically affects data availability, which I'll touch on briefly in the next slide. And then, of course, we're calculating the availability, and then we also have the calibration validation control. So we have the expected values, then we have the actual values that we collect, and you can also press the button to change those values, run a calibration, or schedule the calibrations to be automatically run daily. So you don't actually, it can be operator hands off, and you'll just get an alarm in case something goes wrong. And if everything's working, then there's really very low maintenance type of application. As well as there's certain statuses on the right and kind of pressure stuff at the bottom as well, but all that is customized based on the facility where this system's running. Briefly touched on the SO2 calculation. So those are required by and driven by the regulatory compliance. So in case of the Canadian regulations, the SO2 was calculated with the assumption of 98% combustion efficiency, where we took the SO2 contribution from H2S, COS, and CS2. CS2 has 2 sulfur molecules, so that's why it's double sulfur from there. And then we divided by the fraction of the SO2, grams per mole, to then calculate the total, estimate total SO2 output for that particular stream or flare. And then, of course, from multiple flares and multiple fuel gases and CO boilers and SRU incinerators, each of them will have the SO2 value, which are then totaled for the facility total SO2 emissions that can be like annually reported as well. And it's something to note when we're talking about regulations, also keep in mind that for the Reg 88 example, we require the SO2 to be corrected for moisture, so dry basis to standardize across facilities, and 0% oxygen. Typically we've seen anywhere like 10 to 15, but in this case, 0% oxygen is something that was required. So this is an example of the trend. So once all the SO2 are calculated, in this case for 3 different flare emissions, then the values can be also trended, and various alarms, you can see at the bottom, it's probably too small to see, but various alarms are generated based on these regulatory parameters. And then the NHV was also calculated. The NHV is calculated based on the molar fraction of each species that contributes to the heating value times the heating value of the species, and that would be the total BTU per scuff for that flare. And this is why having something like a mass spectrometer, you're able to speciate very accurately, so you're able to then calculate the NHV without requiring any additional calorimeters or anything like that. This table illustrates some of the averages that were calculated. So for this particular regulation, the 10-second was the raw measured value, and then all the averages were built recursively to 1 minute, 15 minute, 1 hour, 3 hour, 12 hour, 1 day, 7 day, and 365 day. And each of those averages had various validation rules. So for example, when we're talking about US EPA Part 60, you need 4 valid 15-minute averages to create a 1-hour average. Versus for the new Reg 88, the new Canadian regulation, you need 75% of good 1-minute averages to make 1-hour average. All right, so when you need to have at least 45 1-minute valid points to build a valid 1 hour. And then based on those, hourly mass was calculated. So you have pounds per hour, the mass rate, and then you can have the total mass of, say, for example, tons per day, per year, and annual total. So when we're talking about previously about availability, that's one of the most important things when it comes to regulatory compliance for CEMS. The target availability for these systems is 95%. So what that basically means is the fraction of analyzer uptime divided the total source operating time times 100. So if your incinerator is running or your flare is running and it's operating, and for the flare example, they should be run on 24/7. When you have valid data, that means your availability is 100%. As soon as data becomes invalid and you get like an invalid hour, be it because of analyzers and error, or it's disconnected, or you're missing data, or you fail the calibration and you haven't recalibrated, that data becomes invalid and that starts driving down your availability percentage. Also note there are some exemptions for daily quality assurance procedures. So the first calibration of the day gets some sort of exemption. So the first hour that you're doing the analyzer validation, and validation calibrations use interchangeably, but really it needs to be daily validation, and then if you fail it, then you calibrate it. For the daily validation, you usually have like a 1 hour that you can run that without that affecting your availability, but obviously you can't just be validating for the whole day. You actually need real measured data from the stack that needs to be quality assured, which is the whole point of a CEMS. And this is one illustration of a quarterly calibration report. So every day we would run a validation at each of the analyzers. And then we would generate a report that can be submitted for regulatory compliance to see when the analyzer drifted. Yellow would be warning, so that's typically 2% on this slide. If you're between over 2% but under 5%, you would have a warning that you're approaching a limit. As soon as you hit 5%, you're out of control, the data becomes invalid until you recalibrate, and the out of control alarm is generated. So for these validations, you typically need to run them daily, and then you also have to do a root cause analysis if you failed, and then you can backfill the data as well. There's a lot of intricacies about these regulations that we can't cover in a simple session like that. But drift would be one of the main KPIs, and then a bunch of other different KPIs were generated, like mean drift, response time, standard deviation. So lower standard deviation will represent a better stability, versus if you have a high standard deviation, something to investigate why your validations are jumping all over. And then this is where you would have the analysis, and then you need to service the system and see what's happening with it. Some of the alarms that were created, total alarm time, alarm frequency, mean time of alarm, like average time of alarm, mean time between alarms. So all these different KPIs can be used to further analyze the health of your CEMS and to see where you would need to investigate it. And then you can generate reports and drill down on any specific analyzer or any specific time period. And whenever an alarm is generated, typical procedures for the operator to acknowledge it and submit like a reason, action, and a comment, which can then be used to further investigate the root cause, perform the root cause analysis, as well as show it in case of a system audit. You're able to go through the system and show the auditor how the system was performing and various deviations and the quality assurance for that system. And this is where the reporting, having all that data in the report is very important, and the electronic operator logbook is important as well to track all the changes to the system. In this case, even for all the formulas, because the data is calculated on the fly, if there was an issue, if you found an issue with one of the previous formulas I showed you, you can always go and change the formula, and all the data will be backfilled automatically and recalculated without having to service the system, and the auditor could see that reflected in the operator logbook. So this concludes my presentation. Hope it was insightful about CEMS and how to properly maintain a CEMS for a complex SO2 reduction project. And if you have any questions.
Thank you, Serge. Any questions? Everybody's ready for a break? Okay. Thank you very much, Serge. We are back on track-ish, and the app has been updated to reflect the original program. So that means a slightly shorter break than was originally planned. It'll be about half an hour, which means we reconvene at 3:15. So back here at 3:15, please. Thank you, everyone.